Hello everybody, Mr. Hennon here, and I want to take another look at the first law of thermodynamics. And what I mean by this is, yes, I know that we've got a general equation for it. The first law basically says that the difference in internal energy is equal to the Q, the heat flowing in or out, minus the work being done or on the gas. So let's try a different example here where we've got the second law written right here. Whoops, let's go back. You're not supposed to see that. Where I have the second law written right here, or the first law, sorry. And one of the things that we learned in the last chapter is that you can find the internal energy of something by taking 3/2 nRT, or you could find the internal energy with 3/2 nKT, or you could find the internal energy with 3/2 P times V. So we actually have a way of finding internal energy. So let's say that I have 3 moles of some kind of monatomic gas, and it's reduced from 540 Kelvin to 350 Kelvin as 5,500 joules of heat flows into the gas. I want to try to find the change in internal energy and the work. Okay, so I'm going to start off by finding the change in internal energy, but I'm not going to use this equation yet. Instead, we're going to jump over here. We're going to use this instead. And so I have N, I have T's, and I'm going to try to figure out what U is, but I'm trying to find the change in internal energy. So the change in internal energy would be 3/2 your number of moles times the ideal gas law constant, and then this would be times your change in temperature. Because we're not changing the number of moles, we're going to talk about sealed containers, but the idea is internal energy is going to happen when we are actually changing the temperature of something. So our change in internal energy would be 3/2 the number of moles, which is 3, the ideal gas law constant, 8.31, and then our change in temperature, we're going from 540 down to 350, so that would be 190 Kelvin. But it's going from 540 down to 350, so we'd actually do final minus initial. We're not going to do high temperature minus low temperature anymore, because I need to know, is the internal energy decreasing or increasing? Now they give us the clue that it's reduced, and we could just realize that, but it might help to actually put a negative sign on there to find this. We should get a change in internal energy that is negative when we actually calculate this. So pull out my handy dandy calculator. I have 3/2, whoops. I have 3/2 times 3 times 8.31 times negative 190. And I get negative 710505. Joules, because that's energy. So now we want to figure out the work. So my equation is right here. Now we're going to actually apply the first law. And so this is part A. Now we're going to apply the first law, but I'm going to rearrange it to solve for work. We know that change in internal energy equals Q minus W. So the W would actually equal Q minus your change in internal energy. But here's what's going to be important is 5,500 joules of heat flows into the gas. So if heat is added to it, that's going to be a positive number. So this will be a positive 5,500 joules. And then over here, I'm subtracting my change in internal energy, but it's a negative. So I'm subtracting a negative 7105.05 to actually find this. And this will find the work when we do this. So it's subtracting a negative. It's actually very important. The signs are going to be extremely important now. So I take my 5,500 minus this answer, and I get 12,605.05. I'm just writing all the numbers for right now. Now, it's a positive number. So if you notice in the problem, they already said that work is done by the gas. And we talked about that. Basically, what's happening is we're having heat flow into this system. Okay, so heat is flowing into the system and the internal energy decreases. The internal energy decreases because it's pushing against its environment. And when it pushes against its environment, it's going to actually cause the thing to try to expand if it can. But when it does that, that's actually working on its environment or on the surroundings. That is work done by the gas. That's positive work. This is the opposite of what chemists do. Physicists talk about work being done by the gas on the surroundings as positive, and when the surroundings do work on your gas and cause them to try to shrink in volume, then that is being done on the gas, and that's negative work. Let's see what we've got for our answers. Sure enough, negative 7,100 and positive 12,600. Try this out. I want to give you a problem to try it out and see if you can find this same kind of stuff. Hope you enjoyed this little edition of the Henstitute Notes.